Welcome to part 2 of modeling defects in silicon solar cells. Why do we want to model solar cells? Think about it. High efficiency or high quality solar cells are not easy or cheap to manufacture. A lot of high energy and high cost processes are necessary to make quality silicon solar cells. If we can better predict how a set of materials will perform, we can steer research in the right direction to prevent a waste of time, money, and resources. Using modeling software makes it relatively easy to narrow down the limits of materials and also play around with defects, electrical and optical properties, and so on. In terms of solar cells, a computational model allows us to quickly predict device performance characteristics by simultaneously solving the coupled differential equations that define semiconductor transport. Our two continuity equations that account for the conservation of free charge carriers, electrons, and holes, where Q is charge, J is carrier flux, G is the rate of carrier generation per volume, and U is the rate of carrier recombination per volume. Then we have Poisson's equation that describes the electrostatic potential, where phi is the electrostatic potential, and epsilon sub s is the dielectric permittivity of a semiconductor, and rho sub fixed is the local density of fixed charge. In this video, I will be demonstrating how we can model defects by using the educational one-dimensional device simulation program called AMPS, Analysis of Microelectronic and Photonic Structures. This simulator was created to allow users to learn how material properties in device design and structure work together to control device physics under various temperatures, spectra, or impressed voltages. I will be using the free version of this software, which can be downloaded from this link. Also, if I refer to any tables or figures from a text, I'm referring to this book, Handbook of Photovoltaic Science and Engineering. To understand how to implement defects into an AMPS model, we will first look at modeling a basic monocrystalline silicon homojunction. Then we will compare it with a device that is already designed and comes with the AMPS software when you download it. First, let's look at some input parameters that we will keep constant, because they are not really material dependent. Under the Ambient tab, we will keep the temperature at 300 Kelvin. We also want to turn on the light and select our incident spectra file to be AM 1.5. We can also check the quantum efficiency box and select the QE file that is used to select a range of wavelengths at which quantum efficiency is calculated. We will keep our contact parameters constant such that we ignore the barrier heights at the contacts by leaving this box unchecked. Then we will consider surface recombination velocities to be on the order of 100 for majority carriers and on the order of 1 for minority carriers. RF is the reflection coefficient. At the front surface, we will leave it at 0, and at the back surface, we will leave it at 1. This assumes that none of the light is reflected out of the cell, and that any light that reaches the back surface will be reflected back into the material. Finally, we select our range of bias voltages such that we can solve our semiconductor transport equations at a specified range of voltages. This allows us to set large voltage steps while we are near the short circuit and very small voltage steps sizes closer to the open circuit. We do this to reduce computational costs because we know the current doesn't really change over a long range of voltages. Under our Materials tab, I've created a 350 nanometer thick N-type emitter and a 300 micron P-type base, based on the device described by Table 3.2 in the text. For silicon, we have a permittivity of 11.7, a band gap of 1.12, an electron affinity of 4.05, density of states for the electron and valence bands on the order of 10 to the 19th. The electron and hole mobilities are different for the N and P type based on the doping densities. The top junction is sufficiently doped to conduct away the generated carriers without resistive losses. However, excessive doping levels can reduce the material's quality, such that the carriers recombine before reaching the junction. In the base layer, a higher doping density leads to a higher open circuit voltage and lower resistance. However, if doping levels are too high, this could result in damage to the crystal. Under the optical properties, I've used data on silicon from PV Education. For the current cell without any defects, we can obtain an efficiency of about 29%, with an open circuit voltage of 0.819 volts and a short circuit current of about 41.4 milliamps per centimeter squared, and a fill factor of 86%. For this cell, the emitter had a donor doping density on the order of 10 to the 19th, and the base had an acceptor doping density on the order of 10 to the 16th. As we know, dopants are technically impurities, which are defects. Now, if we maintain the same original base doping, but reduce the emitter doping, we retain nearly the same short-circuit current, open circuit voltage, and fill factor, which again yields an efficiency around 29.2%. Now let's see what happens if we further reduce the doping densities in both the emitter and the base. Carrier mobilities are dependent on the doping densities. At low impurity levels, the mobility is governed by intrinsic lattice scattering, and at high levels, the mobility is governed by ionized impurity scattering. Carrier mobilities in silicon at 300 Kelvin are well approximated by these equations, 3.60 and 3.61 in the text, as well as figure 3.12. When we adjust this model to account for the change in emitter dopant density, we can still see that the results are pretty much the same. So now let's account for the change in hole and electron mobilities if we decrease the dopant density to the order of 10 to the 16th. Our electron mobility is now an order of magnitude greater. As you can see, this reduced our open circuit voltage. Therefore, when you are changing the dopant density, you need to make sure that you account for the change in hole and electron mobilities. We already know that dopants are necessary for a homojunction to actually work, so let's take a look at the Defects tab. Under Defects, we can define the type of defect. Donor-like, meaning its energy levels are closer to that of the conduction band energy, or acceptor-like, meaning the defect energy level is closer to the valence band energy. We can also define the density of the defect and its location and dispersion within the bandgap, as discrete levels, banded, or Gaussian. We can also define the capture cross-sections. These are like the size of the target for incoming carriers. AMPS allows us to model doping levels and other defect states as localized states that form a continuum throughout the bandgap. These continuous distributions are different from the discrete or banded localized gap states, which only exist at specific energies or at a specific range of energies in the gap. Here's an example of the densities of states for hydrogenated amorphous silicon. The shaded areas indicate these delocalized states in the bands. These bands themselves have tails of localized states with an exponential distribution. Midway between the bands are levels belonging to defects such as dangling silicon bonds. Under the Defects tab, we see that there are also these band tails that we can check off for the conduction and valence bands, and also mid-gap states, like for dangling silicon bonds. In the AMPS program, there's already a prepared device for amorphous silicon PIN structure. If we take a look at this, we can see how they have applied defects in terms of donor and acceptor-like defects, how they are all Gaussian distributions, and also how they include band tails. Many people have used AMPS software to model amorphous silicon in a similar way. In these works, they use input parameters based on experimental results from time-of-flight measurements. For example, one group who was studying hydrogenated amorphous silicon used AMPS to show that hole drift mobility measurements and measurements of temperature dependence of the open circuit voltage could be used to estimate parameters. Similarly, another group studied the effect of wide bandgap p-type hydrogenated nanocrystalline silicon on the performance of amorphous silicon using AMPS. In this video, we briefly discussed some of the defect parameters involved in the AMPS modeling software. If you are interested in exploring the defect parameters involved with AMPS further, when you download the program, check out some of their devices that already come pre-downloaded with the software. When you click the Load button, you can see under the Device tab, there are a lot of different devices already pre-built for you to explore. There are a lot of different thin film types, and then we also have some various amorphous silicon devices. Thanks for watching part 2 of my video on defects in silicon solar cells. I hope you learned something, and if not, then check out these resources.